Hello, and welcome to Space for Sleep. The sun looks calm only because we are protected from almost everything it is doing. From Earth's surface, the sun can feel simple: a bright disk in the morning, warmth on skin, daylight through a window, the ordinary rhythm by which days begin and end. But that simplicity is an illusion created by distance, atmosphere, magnetic protection, and habit. The sun is not a lamp. It is a star, a self-gravitating sphere of plasma more than 1,000,000 kilometers wide, containing almost all the mass in the solar system, converting matter into energy in its core, twisting magnetic fields through its outer layers, and sending a continuous wind of charged particles into space. Everything on Earth depends on this star. The water cycle, the weather, the climate system, the oxygen produced by photosynthesis, the food chain, the chemistry of the atmosphere, the power stored in ancient fossil fuels, and the conditions that made complex life possible are all tied, directly or indirectly, to sunlight. The sun does not merely illuminate Earth. It drives the physical environment in which Earth exists. And yet the same star that makes Earth habitable is also capable of disturbing the technological world built on that habitability. Solar flares can disrupt radio communication. Coronal mass ejections can shake Earth's magnetic field. Energetic particles can threaten satellites and astronauts. The solar cycle rises and falls, and with it the space weather environment around our planet changes. The sun is steady enough for life, but not perfectly quiet. It is also changing slowly. The sun was dimmer when Earth was young. It is brighter now. It will continue to brighten, long before it becomes a red giant. That slow increase in luminosity will push Earth toward conditions very different from the ones life knows today. The sun gives us everything, but it does not promise permanence. To understand the sun is to understand the central engine of our solar system: how it formed, how it burns, how its magnetic field behaves, how it shapes the heliosphere, how it affects Earth, and how it will eventually change the future of every planet around it. The first thing to understand about the sun is scale. The sun is so familiar that the mind tends to shrink it. It becomes a circle in the sky, an object you can cover with a thumb, a presence associated with weather rather than astronomy. But the smallness is purely visual. The sun is about 109 times wider than Earth. More than 1,000,000 Earths could fit inside its volume. Its mass is about 333,000 times Earth's mass, and that mass dominates the entire solar system. This dominance is not poetic. It is mechanical. The planets orbit because the sun's gravity defines the gravitational architecture of the system. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, the Kuiper Belt, most comets, and the distant icy bodies whose long orbits reach toward the edge of the sun's influence all exist inside the gravitational field of one star. The planets are not separate from the sun in any meaningful dynamical sense. They are the sun's surrounding system. The sun also defines time. A year is Earth's orbit around it. Seasons are caused by Earth's tilted rotation axis, as that orbit carries different hemispheres toward and away from sunlight. Day and night are produced by Earth's rotation beneath the star's steady illumination. Ancient calendars, agriculture, migration, sleep, flowering, weather patterns, ocean currents, and human culture all grew around cycles ultimately tied to the relationship between Earth and the sun. And yet Earth intercepts only a tiny fraction of the sun's output. The sun radiates in all directions, almost all of its energy disappearing into space. Earth is simply a small target at 1 astronomical unit, catching less than 1 part in 2 billion of the total energy. That small intercepted fraction is enough to drive the biosphere, the atmosphere, the oceans, and almost every visible form of activity on the planet's surface. The sun is therefore both ordinary and overwhelming. Ordinary, Because the Milky Way contains billions of stars not fundamentally unlike it. Overwhelming, because for Earth it is the central physical fact. Everything else in the solar system is small beside it. Calling the Sun ordinary is not an insult. It is one of the most useful facts about it. Because the Sun is close, bright, and stable, it has become the reference star against which other stars are measured. Stellar luminosities are often given in solar units. Stellar masses are measured in solar masses. Stellar radii are compared to the solar radius. The Sun is not the most massive, not the brightest, not the oldest, not the youngest, not the most violent, not the most unusual, but it is the star we can study in the greatest detail. A distant star is often a point of light. The Sun is a resolved surface, a changing atmosphere, a magnetic system, a particle source, a laboratory. We can observe its granulation, track sunspots across its face, measure vibrations that reveal its interior, detect neutrinos from its core, sample its wind with spacecraft, and watch magnetic loops rise and reconnect in its corona. For stellar physics, the Sun is both a specific star and a calibration instrument for understanding all stars. Its ordinariness also matters for life beyond Earth. If the Sun were a rare type of star, Earth might seem like the product of an exceptional environment. But Sun-like stars are common enough that the processes we see here, protoplanetary disk formation, rocky planets, long main sequence stability, magnetic cycles, stellar winds, and gradual brightening, are not isolated curiosities. They are part of a wider class of stellar behavior. Understanding the Sun helps astronomers understand the conditions around many other stars where planets may orbit. But ordinary does not mean simple. A G-type main sequence star is an enormous plasma system governed by gravity, nuclear physics, radiation transport, fluid dynamics, magnetism, particle acceleration, turbulence, and long-term stellar evolution. The Sun is ordinary only in the way an ocean is ordinary on a water planet. Familiar because it is everywhere, complex because it is real. The Sun is, by the standards of the galaxy, an entirely ordinary star. This statement carries more weight than it might initially seem to, because understanding the Sun well enough to classify it as ordinary, to place it correctly within the vast diversity of stellar objects visible in the Milky Way, required centuries of observation and a revolution in how scientists understand matter and energy. The Sun has a spectral classification of G2V, a designation from a system developed in the early 20th century that encodes information about a star's surface temperature, luminosity, and evolutionary stage in a compact label. The G means it is a yellow dwarf, though as noted in other contexts, yellow is somewhat misleading. The Sun emits light across the entire visible spectrum, appearing white from space, with its apparent yellowish color from Earth's surface being partly an atmospheric effect. The 2 specifies its temperature within the G class, and the V indicates it is a main sequence star, one that is currently in the primary phase of its life, burning hydrogen in its core through nuclear fusion. Main sequence stars are sometimes called dwarf stars in astronomical nomenclature, not because they are particularly small, but to distinguish them from the evolved giant and supergiant stars they will eventually become or that exist in their thousands throughout the galaxy. The Sun formed approximately 4.6 billion years ago in an event that was not particularly unusual for the Milky Way. A region of a molecular cloud, a vast, cold complex of gas and dust, became gravitationally unstable, perhaps triggered into collapse by the shock wave from a nearby supernova, and began to condense. As the cloud collapsed, it fragmented into multiple dense cores, each of which would give rise to a star or stellar system. One such fragment was the proto-Sun, a gradually contracting ball of gas, roughly 75% hydrogen and 25% helium by mass, with traces of heavier elements. that began to heat as gravitational potential energy was converted to thermal energy. Over roughly 50 million years, the proto-sun contracted from a diffuse cloud to a much denser object called a protostar, still not yet hot enough at its core for sustained nuclear fusion, but radiating energy from the heat of contraction. Around it, the remaining material that hadn't fallen directly into the protostar formed a flattened disk, the solar nebula, from which the planets eventually assembled. As the proto-sun continued to contract, its core temperature and pressure rose. At roughly 10 million Kelvin, 10 million degrees Celsius, the density and temperature were sufficient for hydrogen nuclei to overcome their mutual electromagnetic repulsion and fuse together, initiating the nuclear reactions that have powered the sun for 4.5 billion years and will continue for roughly another 5 billion. This moment, the ignition of hydrogen fusion, is sometimes described as the sun's birth, the transition from contracting protostar to genuine, stable star. With fusion ignited, the outward pressure generated by the energy released from nuclear reactions balanced the inward pull of gravity, and the sun reached a new, stable equilibrium. It has maintained this equilibrium with remarkable precision ever since. To understand how the sun generates its energy, it is worth understanding nuclear fusion at least in outline, because the physics involved is genuinely counterintuitive and genuinely remarkable. At the sun's core, temperatures hover around 15 million Kelvin and the density is roughly 150 grams per cubic centimeter, about 13 times the density of lead. Under these conditions, hydrogen atoms exist not as complete atoms with electrons orbiting nuclei, but as a plasma. The extreme temperature strips the electrons completely free from the nuclei, leaving a mixture of bare protons, hydrogen nuclei, and electrons moving at enormous speeds, colliding with each other constantly. The primary fusion process in the sun is the proton-proton chain, a series of nuclear reactions in which 4 hydrogen nuclei, for protons, are converted into one helium-4 nucleus, 2 positrons, 2 neutrinos, and energy in the form of gamma-ray photons. The net result is that 4 protons, with a combined mass slightly greater than the resulting helium-4 nucleus, are transformed into one helium-4 nucleus plus energy, with the mass difference converted to energy according to Einstein's famous equation, E=mc². The amount of energy per reaction is tiny by human standards, about 4 times 10 to the minus 12 joules per proton-proton chain completion. But the sun has roughly 1.5 times 10 to the 57th protons in its core available for fusion, and reactions occur at an enormous rate, with the net result that approximately 3.8 times 10 to the 26th watts of energy are produced, the solar luminosity, a number so large it is essentially meaningless without context. For context, the total amount of energy consumed by all of human civilization in a year is roughly 6 times 10 to the 20th joules. The sun produces that much energy in roughly 25 milliseconds. Every second, the sun converts about 4 million metric tons of its own mass into energy through this process. In the 4.5 billion years it has been burning, the sun has converted approximately 100 Earth masses of material into pure energy. The proton-proton chain, despite its cosmic importance, is actually extraordinarily inefficient when measured per unit of reacting material. At any given moment, the probability that any specific pair of protons in the sun's core will fuse in the next second is vanishingly small. The temperature is just barely sufficient, statistically speaking, for quantum tunneling to allow protons to occasionally breach the electromagnetic barrier that would otherwise prevent their fusion. The sun's energy output is maintained not by rapid, efficient burning of its fuel, but by the sheer number of opportunities for the rare event to occur across the enormous quantity of material in its core. If the conditions were different, if the sun were somewhat larger, with a hotter core, the reactions would proceed faster, but the star's lifetime would be correspondingly shorter. The Sun's particular mass gives it a main sequence lifetime of roughly 10 billion years, which happens to be comfortably long enough for complex life to have had time to evolve on an orbiting planet. The energy released from the core does not travel to the surface quickly. Gamma-ray photons produced by nuclear reactions at the core are immediately absorbed by surrounding plasma, re-emitted, absorbed again, scattered, and re-emitted repeatedly in a process called radiative diffusion that is extraordinarily slow. A photon does not travel in a straight line from core to surface. It takes a random walk path through the solar interior, being absorbed and re-emitted roughly every centimeter, with each re-emission sending it in a random direction. The net result is that energy produced at the Sun's core takes between 10,000 and 170,000 years to work its way to the surface, depending on which estimate of the Sun's opacity is used, gradually being reprocessed from high-energy gamma rays to the lower-energy visible light we see, through countless absorptions and re-emissions along the way. When you step outside on a sunny day and feel the warmth of sunlight on your skin, you are absorbing photons that began their journey deep within the Sun's core between 10,000 and 100,000 years ago, during the Pleistocene epoch on Earth, when mammoths roamed the northern continents. They have spent most of their existence diffusing through the solar interior, then about 8 minutes crossing the distance from the Sun's surface to Earth's surface. That 8-minute light travel is the last, swift leg of what was, for each photon, an extraordinarily long and tortuous journey. There is a quiet subtlety in the Sun's fusion that is easy to miss. The Sun is not exploding. It is not burning chemically. It is not consuming fuel the way a fire consumes wood. It is balanced. Gravity compresses the core. Fusion releases energy. That energy creates pressure, and pressure resists gravity. If the core produces slightly too much energy, it expands a little, cools a little, and fusion slows. If it produces too little, gravity contracts the core a little, temperature rises, and fusion increases. This negative feedback is what makes the Sun stable over billions of years. This stability is not perfect stillness. The Sun vibrates, convects, rotates differentially, cycles magnetically, and changes slowly as hydrogen becomes helium in its core. But the central balance between gravity and pressure is extraordinarily reliable. A star like the Sun can shine for about 10 billion years because its mass places it in a stable middle category. Not so small that fusion barely begins, not so massive that it burns violently and dies quickly. Massive stars may exhaust their fuel in a few million years. Red dwarfs may last for trillions. The Sun sits between those extremes, long-lived enough for biology to become complex, but energetic enough to keep Earth warm. This is one of the most important coincidences in the story of life on Earth. The timescale of solar stability is long enough for oceans, chemistry, evolution, oxygenation, multicellular organisms, intelligence, and technology. Had the Sun been much more massive, Earth might have had heat and light, but not time. Had it been much smaller and dimmer, Earth would have needed to orbit much closer, exposed to stronger tidal locking and a different flare environment. The Sun's ordinary mass is, from Earth's point of view, an extraordinary gift of duration. Fusion in the core is also slow in a way that surprises people. The power generated per unit volume in the Sun's core is not comparable to a bomb. It is closer to the heat production of a compost pile. The core is powerful because it is enormous. The Sun shines not because each cubic meter is violently explosive, but because an immense mass of plasma is producing energy steadily across a vast central region. Stellar power is patience multiplied by size. The journey of sunlight is one of the strangest journeys in the solar system. A photon created in the core does not simply fly outward. In the dense plasma of the interior, it is absorbed and re-emitted again and again, scattered through a random walk so tangled that the energy may take tens of thousands of years, perhaps longer depending on the modeling details, to reach the photosphere. By the time it escapes as visible light, it is no longer the same gamma-ray photon produced by fusion. The energy has been redistributed through countless interactions, softened from high-energy radiation into the broad spectrum of sunlight. Then, suddenly, the last leg is fast. Once light leaves the photosphere, it crosses the vacuum to Earth in about 8 minutes and 20 seconds. The energy may have wandered inside the sun for longer than human civilization has existed, then crossed the gap between star and planet in the time it takes to drink a cup of tea. This means daylight is both ancient and immediate. Ancient, because the energy began in the deep interior long before it reached the surface. Immediate, because the sunlight falling on leaves, ocean water, skin, glass, desert sand, or snow has just completed the open space part of its journey. We experience the final few minutes of a process that began far below the visible surface. Under pressure and temperature, no human machine can reproduce on that scale. The sun therefore connects two kinds of time: the slow time of stellar interiors and the fast time of human mornings. The sun's structure is layered, each region characterized by different physics, different temperatures, and different processes. At the center is the core, extending to roughly 25% of the sun's total radius, about 175,000 kilometers. This is where essentially all the sun's energy is produced. The temperature here is 15 million Kelvin, the density about 150 grams per cubic centimeter, and the pressure is approximately 250 billion times Earth's atmospheric pressure. The core contains about 50% of the sun's mass within 25% of its radius, reflecting the steep increase in density toward the center. Surrounding the core is the radiative zone, extending from roughly 25 to 70% of the sun's radius. Energy produced in the core moves outward through this region by radiation, the slow, random walk diffusion of photons described above. The temperature here ranges from 15 million Kelvin at the base to about 2 million Kelvin at the top. The material here is hot, dense plasma, still predominantly in the form of bare atomic nuclei and electrons. At approximately 70% of the solar radius, the physics changes qualitatively. The temperature has dropped to the point where heavier elements, particularly oxygen, carbon, nitrogen, and heavier atoms, can capture electrons and become partially ionized rather than completely stripped. These partially ionized atoms absorb radiation much more efficiently than the completely ionized plasma below, making the material more opaque to outgoing radiation and causing a backup of energy. This increased opacity triggers convective instability. The hot plasma near the base of this region becomes buoyant relative to the cooler, denser plasma above and begins to rise. The resulting convective overturning, cells of hot plasma rising, cooling, and falling back down in a cycle similar in principle to the circulation of water heated in a pot, carries energy outward through the convection zone more efficiently than radiation alone could manage. The convection zone extends from roughly 70% of the solar radius to the visible surface. The convective cells range in scale from the enormous, large-scale circulation patterns thousands of kilometers across to the small, individual granules visible at the solar surface through high-resolution telescopes. A single solar convective granule, one rising cell of hot plasma, is typically about 1,000 kilometers across and lasts for perhaps 10 minutes before the cooled plasma from its edges sinks back down and the cell is replaced by a new one rising beneath it. At any moment, the sun's visible surface is covered in roughly 4 million of these granules, forming a constantly changing, seething pattern of rising bright centers and darker, sinking edges that can be clearly resolved with modern solar telescopes. The visible surface of the Sun, called the photosphere, from the Greek for light sphere, is the level at which the plasma becomes transparent enough for photons to escape freely into space. The photosphere is about 500 kilometers thick, with an effective temperature of about 5,777 Kelvin, which corresponds to the peak of the Sun's electromagnetic emission being in the yellow-green part of the visible spectrum. The photosphere is not a sharp boundary in any physical sense, but rather the level at which the mean free path of photons, the average distance they travel before being absorbed, becomes larger than the Sun itself, allowing them to escape. Above the photosphere are the Sun's outer atmospheric layers, which are genuinely counterintuitive in their thermal properties. Moving outward from the photosphere, temperature should, by the simple logic of moving away from a heat source, decrease. For a short distance, it does. There is a layer called the chromosphere, from about 500 to 2,000 kilometers above the photosphere, where temperature initially drops to about 4,000 Kelvin before, surprisingly, rising again. Above the chromosphere is a thin transition region just a few hundred kilometers thick, where temperature rises extremely rapidly, from around 20,000 Kelvin to 1,000,000 Kelvin within a distance smaller than many cities on Earth's surface. And above the transition region is the corona, the Sun's outer atmosphere, extending millions of kilometers into space, with temperatures of 1 to 3 million Kelvin, far hotter than the photosphere below. This temperature inversion, the corona being orders of magnitude hotter than the surface, is the coronal heating problem, one of the most celebrated unsolved puzzles in solar physics. The second law of thermodynamics doesn't strictly forbid it. Heat doesn't have to flow from hot to cold in a system actively being driven by a non-thermal energy source. But the corona's extreme temperature demands explanation. What mechanism is continuously depositing enough energy into the corona to maintain it at 1,000,000 degrees against the constant energy losses to radiation and to the solar wind that flows outward from it? The two leading proposed mechanisms are wave heating and nanoflare heating. Wave heating proposes that magnetohydrodynamic waves, waves in the plasma driven by convective motions below the photosphere, propagating along magnetic field lines into the corona, carry energy upward and deposit it there through wave dissipation or mode coupling, transferring the mechanical energy of the waves into thermal energy of the coronal plasma. Nanoflare heating, proposed by the solar physicist Eugene Parker in 1988, suggests that the corona is continuously being heated by enormous numbers of very small, individually unobservable energy release events, called nanoflares, resulting from the constant tangling and reconnection of magnetic field lines threading through the corona, driven by the shuffling of their foot points by convective motions in the photosphere below. Each individual nanoflare is too small to detect, but the cumulative effect of billions of them occurring continuously might provide the sustained energy input needed to maintain the corona at its observed temperature. Distinguishing between these mechanisms observationally requires measurements at spatial and temporal resolutions difficult to achieve from Earth or from current spacecraft. The Parker Solar Probe, launched in 2018 and designed to approach within about 9 solar radii of the Sun's center, far closer than any previous spacecraft, is providing new data on the near-Sun environment that is beginning to constrain the competing models. Its observations of rapid fluctuations in the solar wind's velocity and magnetic field, called switchbacks, appear consistent with wave heating models, but the full picture is still being assembled. Understanding coronal heating is not just a matter of academic curiosity. The corona is the source of the solar wind, the stream of charged particles that flows outward through the solar system, and whose properties influence everything from auroral displays on Earth to the radiation environment experienced by spacecraft and astronauts. The magnetic field turns the sun from a steady furnace into a changing star. Without magnetism, the sun would still shine. Fusion would still power it, the photosphere would still glow, and Earth would still receive sunlight. But the sun would be far less dynamic. Sunspots, flares, coronal loops, prominences, coronal mass ejections, and much of the structure of the corona are magnetic phenomena. The sun's visible light is dominated by thermal radiation from hot plasma, but its drama is magnetic. This is also why solar physics is difficult. Magnetic fields in plasma do not behave like simple lines drawn through empty space. Plasma is electrically conducting, so it drags magnetic fields with it. Magnetic fields guide plasma, confine plasma, accelerate plasma, and sometimes reconnect explosively. The result is a feedback loop. Moving plasma builds magnetic fields. Magnetic fields shape plasma motion, and the combined system becomes turbulent, structured, and often unpredictable. The sun is therefore not only a problem in nuclear physics. It is a problem in magnetohydrodynamics, the physics of magnetic fields in electrically conducting fluids. It is a laboratory larger than 1,000,000 Earths, running continuously, generating phenomena no laboratory on Earth can reproduce at full scale. This is why the 11-year cycle is both regular and irregular. The cycle is visible enough that astronomers can count sunspots and identify maxima and minima, but the details of any single cycle are not perfectly predictable. Some cycles are strong, some are weak. Some maxima are double-peaked. Some active regions produce enormous eruptions, while others remain comparatively quiet despite complex magnetic structure. The sun is ordered enough to have a cycle, but chaotic enough to surprise us. The sun's magnetic field is the thread connecting nearly all of its dynamic phenomena: sunspots, solar flares, coronal mass ejections, the solar wind, and the roughly 11-year solar cycle. Understanding the solar magnetic field means understanding much of what makes the sun variable and sometimes hazardous to the technology-dependent civilization that orbits it. The sun's magnetic field is not like Earth's, a relatively simple, roughly dipolar field generated by convection in an electrically conducting liquid iron core, oriented approximately along the rotation axis and changing on timescales of hundreds of thousands of years between polarity reversals. The sun's field is generated by a similar basic dynamo process: convection in an electrically conducting plasma, converting kinetic energy of plasma motion into magnetic energy, but in a far more complex, more dynamic, and more rapidly evolving way. The critical difference arises from the sun's differential rotation. Unlike a solid body, the sun does not rotate as a unit. Different latitudes rotate at different rates. The equatorial region of the sun completes one rotation in approximately 25 days, while the polar regions take about 35 days. This differential rotation, combined with the convective motions that carry plasma across the boundary between the radiative zone and convection zone, a region called the tachocline, continuously deforms and amplifies the sun's magnetic field. Imagine an initially straightforward dipole magnetic field threading through the sun roughly along its rotation axis. As the equatorial plasma rotates faster than the polar plasma, it drags the magnetic field lines with it, stretching and winding them around the sun in the equatorial plane, a process called the omega effect. Over months to years, these originally roughly north-south field lines become wound into tight bundles oriented roughly east-west, like thick rubber bands under tension. These amplified, wound-up magnetic fields can become so concentrated and strong that they create regions of intense magnetic flux tubes, that can rise through the convection zone by magnetic buoyancy. When such a flux tube pierces the photosphere and emerges through the solar surface, The strong magnetic field in that region suppresses the convective motions that normally carry hot plasma upward from below, slightly cooling that region of the surface. These cooled regions appear darker than the surrounding photosphere. They are sunspots. Sunspots are not actually dark in an absolute sense. They are still at temperatures of roughly 3,500 to 4,500 Kelvin and would appear brilliantly luminous if viewed against a black background. But they appear dark in contrast to the surrounding photosphere at 5,700 Kelvin because the human eye and photographic film naturally normalizes to the average brightness. A large sunspot group can be several times the size of Earth, and the largest ever recorded were many tens of times Earth's diameter. Sunspots typically appear in pairs or groups, with one sunspot carrying a magnetic field pointing outward from the sun and the other carrying field pointing inward, opposite polarities, connected by magnetic field lines arching through the corona above. The field threading through the corona above sunspot groups is where the most energetic events in the solar system originate. As convective motions in the photosphere continue to push and twist the foot points of these coronal magnetic field structures, the field lines become increasingly twisted and stressed, storing magnetic energy like a coiled spring. When the field configuration becomes unstable, when the accumulated magnetic stress exceeds a threshold, the field can undergo rapid magnetic reconnection, a process where adjacent antiparallel field lines snap together and reconnect in a new configuration, releasing the stored magnetic energy explosively. This explosive magnetic reconnection is a solar flare, a sudden brightening of the solar atmosphere at the site of the reconnection, releasing energy equivalent to many billions of nuclear weapons in a matter of seconds to minutes. Most of it initially is X-rays and extreme ultraviolet radiation that travel at the speed of light and arrive at Earth in about 8 minutes. The X-ray burst from a major solar flare can significantly increase the ionization of Earth's upper atmosphere, disrupting high-frequency radio communications that reflect off the ionosphere and are used for long-distance radio transmission and aviation communication over polar routes, effects that can be noticed within minutes of the flare's onset. Frequently accompanying or following flares are coronal mass ejections, the most spectacular manifestations of solar activity. A coronal mass ejection is the explosive expulsion of a large region of the sun's corona, sending billions of tons of magnetized plasma into interplanetary space at speeds ranging from a few hundred to several thousand kilometers per second. These are three-dimensional structures, magnetized plasma clouds expanding outward through the solar system, retaining some of the sun's magnetic field structure as they travel. If a coronal mass ejection happens to be aimed in Earth's direction, it can arrive at Earth in anywhere from 1 to 3 days, depending on its speed, and interact with Earth's magnetic field in an event called a geomagnetic storm. The effects of geomagnetic storms on Earth's technological infrastructure can range from minor to severe. Geomagnetic storms at the lower end of the scale produce enhanced auroral displays, the northern and southern lights extending to lower latitudes than usual, visible perhaps from the northern United States or southern Europe rather than only from Arctic regions. More powerful storms can induce electrical currents in long conductors such as power transmission lines, pipelines, and telegraph cables, disrupting electrical systems and potentially damaging transformers. The most extreme geomagnetic storm in recorded history, the Carrington event of September 1859, produced by an exceptionally powerful coronal mass ejection, induced currents so strong in telegraph lines across North America and Europe that telegraph operators reported receiving electrical shocks, being able to send messages with their equipment disconnected from batteries, and in some cases setting fire to their paper from the currents induced in the wires. Modern power grids, which are far more extensive and interconnected than 19th-century telegraph networks, are potentially far more vulnerable to a Carrington-scale event and the consequences of a major geomagnetic storm for a highly electrified, technology-dependent civilization are a genuine concern that governments and utilities have been gradually developing contingency plans to address. The 11-year solar cycle, the regular rise and fall in solar activity measured by the number of visible sunspots, the frequency of flares, and the rate of coronal mass ejections, reflects the underlying dynamics of the solar magnetic field. At solar minimum, the sun is relatively quiet, with few sunspots and infrequent large flares. As the cycle progresses, sunspot numbers rise, solar activity increases, and the sun's corona becomes more complex and turbulent. At solar maximum, the number of sunspots reaches a peak, large flares and coronal mass ejections are more frequent, and the sun's overall magnetic field is at its most complex and disordered. After solar maximum, activity declines again toward the next minimum, and at this point, the sun's magnetic polarity has reversed. The north and south magnetic poles of the sun have swapped, so that the full magnetic cycle, from one polarity to the same polarity again, takes approximately 22 years, with the 11-year sunspot cycle representing half this magnetic reversal cycle. The mechanism of the polarity reversal, the alpha effect in dynamo theory, involves the Coriolis force acting on rising convective cells in the convection zone, twisting them and imparting a helical motion that gradually rotates the wound-up, amplified magnetic field lines back toward a north-south orientation, but with opposite polarity from where they started, completing the reversal. This process, the alpha effect combined with the differential rotation that drives the omega effect, constitutes what solar physicists call the alpha-omega dynamo, the basic mechanism believed to be responsible for the solar cycle. The heliosphere is the sun's invisible territory. It is not a solid boundary, and it is not defined by light. Sunlight continues far beyond the heliopause. Gravity continues even farther. But the solar wind, flowing outward from the corona, creates a bubble in the surrounding interstellar medium. Inside that bubble, space is shaped primarily by the sun's plasma and magnetic field. Outside it, the local interstellar environment dominates. This means the planets are not orbiting through ordinary interstellar space. They are orbiting inside the sun's extended atmosphere, in a sense. The solar wind is thin beyond imagination by earthly standards, but it is not nothing. It carries particles, magnetic fields, turbulence, and energetic disturbances outward. It shapes comet tails, interacts with planetary magnetospheres, erodes unprotected atmospheres, and helps determine the radiation environment through which spacecraft must travel. The Voyager spacecraft crossing the heliopause did not leave the sun's gravity, and they did not leave the solar system in the sense of escaping all objects orbiting the sun. But they did enter interstellar space in the plasma sense, beyond the region where the solar wind dominates. Their measurements showed that the edge of the heliosphere is not a neat shell but a dynamic boundary, responding to solar activity and interstellar pressure. The sun therefore has more than one edge. There is the visible edge of the photosphere. There is the outer corona. There is the reach of the solar wind. There is the gravitational reach toward the Oort cloud. A star is not just the glowing sphere we see. It is a layered influence extending through space. The solar wind is the constant outward flow of plasma from the sun's corona into interplanetary space, a fundamental feature of the solar system's environment that affects every planet and spacecraft and fills the entire heliosphere. The solar wind was proposed theoretically by Eugene Parker in 1958, based on his calculations showing that the corona, being so hot, cannot be in static gravitational equilibrium. It must be continuously expanding outward at supersonic speeds. Parker's prediction was received with skepticism at the time, but was directly confirmed by measurements from the Mariner 2 spacecraft in 1962, which detected the continuous flow of charged particles in interplanetary space during its journey to Venus. The solar wind is not uniform. It comes in two main varieties, the fast solar wind and the slow solar wind. The fast solar wind, traveling at roughly 700 to 800 kilometers per second, originates primarily from coronal holes, regions of the corona where the magnetic field lines are open, extending outward into interplanetary space rather than looping back to the solar surface. Plasma from these regions can escape freely along the open field lines, flowing outward continuously in relatively unobstructed streams. The slow solar wind, at roughly 300 to 400 kilometers per second, originates from regions surrounding the equatorial streamer belt, a band of closed magnetic field structures around the sun's equator, and has a more complex and less well understood origin than the fast wind. As the solar wind flows outward, it carries the sun's magnetic field with it. The field lines are frozen in to the flowing plasma, in the sense that the highly conductive plasma cannot move across magnetic field lines without dragging them along. Because the sun is rotating, the field lines threading through the outward flowing solar wind are draped into an Archimedean spiral pattern, the Parker spiral, the same shape a garden sprinkler creates as water sprays outward while the sprinkler rotates. Earth's orbit, at 1 astronomical unit, intersects the Parker spiral at an angle of roughly 45 degrees, so that the magnetic field in the solar wind near Earth is typically oriented at about 45 degrees to the radial direction. At Earth's distance, the solar wind arrives with a typical particle density of about 5 protons per cubic centimeter, extraordinarily rarefied by any terrestrial standard, equivalent to a vacuum far better than any that can be achieved in a laboratory, but flowing at hundreds of kilometers per second, representing a substantial flux of particles and momentum. Earth's magnetic field deflects most of this solar wind around the planet, forming the magnetosphere, a bubble of Earth's magnetic influence carved out of the solar wind, with the magnetopause at its outer boundary, where the solar wind pressure balances Earth's magnetic pressure. Without this protective magnetosphere, the solar wind would directly strike Earth's atmosphere, gradually stripping it away through a process similar to what happened to Mars when Mars lost its own magnetic field billions of years ago. The solar wind continues outward through the solar system until it reaches the termination shock, the region, at roughly 80 to 100 astronomical units from the Sun, where the solar wind velocity drops abruptly from supersonic to subsonic as it encounters the pressure of the interstellar medium. Beyond the termination shock is the heliosheath, a turbulent region where the slowed solar wind and the interstellar medium interact. And beyond the heliosheath is the heliopause, the boundary where the solar wind pressure exactly balances the pressure of the interstellar medium, the true outer boundary of the Sun's influence. Voyager 1 crossed the heliopause in 2012, becoming the first human-made object to enter interstellar space, while Voyager 2 made the same crossing in 2018. The entire region within the heliopause, containing all the planets, all the planetary satellites, all the asteroids and comets within 100 astronomical units or so, and all the interplanetary space filled with solar wind, is called the heliosphere. We live inside the Sun's heliosphere, surrounded by solar wind, existing within the Sun's sphere of magnetic and particle influence, which extends to 100 astronomical units in every direction. The Sun doesn't just give us light and heat, it maintains the entire environment within which our solar system exists. It is important to keep solar influence on climate in perspective. The Sun is the ultimate energy source for Earth's climate system, but not every climate change is caused by the Sun. Modern global warming cannot be explained by recent solar variation. The measured changes in solar output over the recent solar cycles are far too small, and the pattern of warming in the atmosphere matches greenhouse gas forcing rather than increased solar brightness. The lower atmosphere has warmed while the stratosphere has cooled, a signature expected when greenhouse gases trap more outgoing infrared radiation, not when the sun simply becomes stronger. This distinction matters because the sun is sometimes used in public discussions as a vague alternative explanation for changes that are actually well understood. The sun drives the climate system, but greenhouse gases change how Earth retains the energy it receives. Both statements can be true at once. Solar physics does not weaken climate science. It helps define the baseline against which human forcing is measured. On geological timescales, however, the sun's evolution is decisive. A slow brightening of roughly 10% per billion years is small from one human lifetime to the next, but enormous over the age of a planet. The faint young sun paradox, the long-term carbon cycle, the eventual moist greenhouse future of Earth, and the differences between Venus, Earth, and Mars all show that stellar evolution and planetary climate cannot be separated. A planet's habitability is a moving target around a changing star. Solar activity directly affects Earth's climate, though the nature and magnitude of this connection is more complex and more nuanced than popular accounts sometimes suggest. The most direct connection is through the total solar irradiance, the total amount of energy per unit area delivered by the sun to Earth's orbit. This quantity varies slightly with the solar cycle. It is about 0.1% higher at solar maximum than at solar minimum, as additional bright regions surrounding active sunspot areas contribute slightly more energy than the sunspots themselves remove. This 0.1% variation is small compared to the roughly 4% of forcing associated with human greenhouse gas emissions since the Industrial Revolution, and climate scientists are confident that solar variability alone cannot explain the warming trend observed over the past several decades. The signature of solar-driven climate variation, which would be expected to warm the lower stratosphere as well as the troposphere, is distinct from the signature of greenhouse gas forcing, which warms the troposphere while cooling the stratosphere, and observed temperature trends are far more consistent with greenhouse gas forcing than with solar variability. On geological timescales, however, solar variability matters enormously. The sun is gradually brightening over its lifetime, increasing in luminosity by roughly 10% per billion years, as the accumulation of helium ash in its core causes the core to contract slightly and run hotter. This gradual increase in solar output has already had profound consequences for the planets of the inner solar system. Venus, as discussed in its own episode, may have been rendered uninhabitable by a combination of its proximity to the sun, its lack of plate tectonics, and the gradually increasing solar luminosity. Mars, once thought to have had a warmer, wetter climate, lost its thick atmosphere and surface water partly through the loss of its magnetic field and the resulting increased solar wind erosion. But the gradual increase in solar ultraviolet radiation also contributed to this drying. And for Earth, the gradually brightening sun has driven changes in the habitable zone over geological time, and will eventually, in roughly 1 billion years, drive Earth's surface temperature above the threshold for liquid water, rendering the planet uninhabitable by most complex life forms even before the sun begins its red giant phase. The faint young sun paradox is a related puzzle that has occupied solar physicists and geologists for decades. The geological record shows that Earth had liquid water on its surface for most of its 4.5 billion year history, including its earliest epochs, when the sun was approximately 20 to 30% less luminous than today. A sun that dim, shining on an Earth otherwise identical to the present, should have produced a frozen planet, temperatures too cold for liquid water. And yet ancient rocks preserve clear evidence of liquid water, even in the earliest Archean. The resolution involves some combination of a denser early atmosphere with more greenhouse gases, particularly methane, carbon dioxide, and possibly other compounds, that provided sufficient warming to compensate for the dimmer sun. The details of exactly how this worked are still being worked out, but the existence of the paradox itself illustrates how intimately the sun's evolution and Earth's habitability are connected. The sun's energy output is not perfectly constant on all timescales. While it is remarkably steady on human historical timescales, varying by less than a fraction of a percent over the 11-year solar cycle, there are periods of extended unusual behavior that have had measurable, if modest, climatic effects. The Maunder minimum, lasting roughly from 1645 to 1715, was a prolonged period of very low sunspot activity in which the sun appeared essentially devoid of its usual cycle of sunspot appearance and disappearance for about 70 years. Astronomical observations from the period, combined with analysis of radioactive carbon-14 and beryllium-10 isotopes preserved in tree rings and ice cores, which are produced by cosmic rays that the sun's magnetic field partially shields Earth from, and which serve as proxies for past solar activity, confirm that this was a real period of suppressed solar activity, not simply a gap in records. The Maunder minimum coincided with the Little Ice Age, a period of somewhat cooler average temperatures in many regions, particularly in Europe and North America, characterized by more frequent and severe winters, advancing glaciers, and disruption of agricultural patterns. Whether the Maunder minimum caused the Little Ice Age, contributed to it, or merely coincided with it due to volcanic and other natural climate variability remains debated, but the correlation is suggestive of at least some solar influence on regional climate on multi-decadal timescales. The Dalton minimum, roughly 1790 to 1820, was a shorter but similarly low activity period, coinciding with several very cold years in the early 19th century, including 1816, the year without a summer, which followed the massive eruption of Mount Tambora in the Dutch East Indies and produced widespread crop failures, famine, and social disruption across the Northern Hemisphere. The relative contributions of the volcanic eruption and the reduced solar activity to the extreme weather of that period have been studied extensively. There is also the Sporer minimum, from roughly 1460 to 1550, another period of suppressed solar activity, and modern paleoclimate reconstructions have identified several other similar grand minima, extending back thousands of years, suggesting that these are a recurring feature of the solar cycle on centennial timescales rather than unusual aberrations. The current solar cycle, Solar Cycle 25, which began in December 2019, has been more active than early predictions suggested. In October 2024, NASA and NOAA announced that the Sun had reached the maximum phase of Solar Cycle 25, a period when sunspots, solar flares, and coronal mass ejections become more frequent. That maximum phase produced several significant space weather events, including the powerful May 2024 geomagnetic storm that generated auroral displays far beyond their usual polar regions. The long-term behavior of the solar cycle, including whether future cycles will be stronger or weaker than current ones, cannot be reliably predicted more than a few cycles in advance with current understanding of the solar dynamo. The detailed study of the Sun's interior, helioseismology, represents one of the more remarkable achievements of late 20th century solar physics, demonstrating that what lies beneath an opaque stellar surface can be probed using the same basic principles that geologists use to map Earth's interior, measuring the propagation of waves. The Sun's surface oscillates. At any given point, the photosphere is rising and falling, bouncing in and out, driven by pressure waves that propagate through the solar interior. These oscillations were first discovered in the early 1960s, when Robert Layton, Robert Noyes, and George Simon observed systematic 5-minute oscillations in the Doppler shift of spectral lines from the solar surface, patterns of rising and falling plasma, with a characteristic period of about 5 minutes. Initially interpreted as a local surface phenomenon, these oscillations were eventually understood to be the superposition of millions of simultaneously excited normal modes of the entire Sun, global standing waves, called P modes, pressure modes, that reflect between the solar surface and various depths within the interior, sampling different layers of the Sun on their way. By measuring the precise frequencies of these oscillations, which depend on the sound speed profile within the Sun, which in turn depends on the temperature, density, and composition profile, helioseismologists have been able to reconstruct the Sun's internal structure with remarkable precision, probing depths far beyond what any other technique can reach. The tachocline, the sharp boundary between the uniformly rotating radiative zone and the differentially rotating convection zone, was discovered through helioseismology before it was properly understood theoretically. The rotation rate of the Sun's interior at different latitudes and depths was mapped in detail, revealing not just the differential rotation at the surface, but also the surprisingly uniform rotation of the radiative zone, which rotates almost as a solid body despite the differential rotation above it. Helioseismology also provided a crucial test of solar models through what was called the solar neutrino problem. Neutrinos, nearly massless particles produced in enormous numbers by the nuclear reactions at the Sun's core, roughly 65 billion solar neutrinos pass through every square centimeter of Earth's surface facing the Sun every second, were measured in pioneering underground experiments beginning in the 1960s by Raymond Davis Jr. and John Bacall. These experiments found only about a third to a half as many solar neutrinos arriving at Earth as the standard solar model predicted should be produced. This discrepancy, the solar neutrino problem, persisted for decades, raising the uncomfortable possibility that either the solar models were wrong or the neutrino physics was wrong. Helioseismology strongly supported the solar models. The helioseismic measurements of the Sun's interior structure were consistent with the standard model's predictions for the temperature and density profile at the core, suggesting the neutrino production rate was indeed as predicted. The problem therefore had to lie in the neutrino physics. The resolution came from the discovery of neutrino oscillations, the quantum mechanical phenomenon by which neutrinos change between different flavors, electron neutrino, muon neutrino, tau neutrino, as they travel, so that electron neutrinos produced at the Sun's core could partially convert to muon or tau neutrinos en route to Earth, and the early experiments, sensitive only to electron neutrinos, were detecting only the fraction that hadn't oscillated away. When experiments sensitive to all neutrino flavors simultaneously were built, most prominently the Sudbury Neutrino Observatory in Canada, they confirmed that the total neutrino flux from the Sun matched the standard model's predictions perfectly. The solar neutrino problem was solved, and in the process, neutrino oscillations were confirmed as a real phenomenon, demonstrating that neutrinos have non-zero mass in contradiction to the original formulation of the standard model of particle physics, contributing directly to revisions of fundamental particle physics theory. Modern solar missions have changed the Sun from a distant object into a place being physically sampled. Parker Solar Probe is not simply taking pictures. Its purpose is to fly through regions where the solar wind is still young, where the corona transitions into the outflowing plasma that fills interplanetary space. The spacecraft carries instruments to measure particles, fields, waves, and dust. It is protected by a heat shield facing temperatures intense enough to destroy ordinary spacecraft materials, while its instruments remain cool enough to operate in the shadow behind that shield. Solar Orbiter approaches the problem differently. Instead of only diving close, it gradually tilts its orbit to see the sun from above and below the plane in which the planets orbit. That matters because the solar poles help control the global magnetic field and the solar cycle. But Earth-based observers see the sun mostly from near its equator. The first high-latitude views returned in 2025 opened a new perspective on the polar magnetic field during a time when the sun's magnetic polarity was tangled and reversing. Together, these missions are doing something earlier solar astronomy could not do. One goes close and samples the environment. The other changes angle and images regions previously hidden from direct view. Combined with older and continuing observatories such as SOHO, SDO, STEREO, and ground-based solar telescopes, they make the sun one of the most continuously monitored astrophysical objects in existence. And yet, even with all this attention, major mysteries remain. Why is the corona so hot? How exactly is the solar wind accelerated? What determines whether an active region produces a harmless flare or a civilization-relevant eruption? How does the deep solar dynamo set the strength of future cycles? The sun is the nearest star, but nearest does not mean solved. The sun's outer atmosphere, the corona, is accessible to direct observation only under unusual circumstances. During a total solar eclipse, when the moon precisely blocks the brilliant photosphere, the corona becomes visible to the naked eye as a pearly white halo surrounding the eclipsed sun, ghostly and ethereal, extending for several solar radii in all directions, its structure shaped by the underlying magnetic field into streamers, loops, and plumes. People who have witnessed a total solar eclipse often describe it as one of the most profoundly moving natural spectacles they have ever experienced, not just for the corona, but for the dramatic darkening of the sky, the appearance of stars in the daytime, the temperature drop, the strange behavior of animals, and the visceral sense of the moon's shadow rushing across the landscape. The coincidence that makes total solar eclipses possible, that the moon and sun appear almost exactly the same angular size in Earth's sky, so that the moon can precisely cover the solar disk without hiding the corona, is not a fundamental law of nature, but a transient accident of geometry. The moon is, as discussed in its own episode, slowly moving away from Earth at about 3.8 centimeters per year. In roughly 600 million years, the moon will be far enough away that it will no longer appear large enough to completely cover the sun from Earth's surface, and total solar eclipses will no longer occur. Humans, or whatever beings inhabit Earth in that distant future, will instead see only annular eclipses, the moon centered on the sun but too small to cover it completely, leaving a ring of the photosphere visible around the lunar silhouette. The scientific value of solar eclipses extends well beyond the aesthetic. Some of the most important early observations in solar physics were made during eclipses. The element helium was discovered in the solar spectrum during the eclipse of 1868. Its spectral lines identified in the corona before the element was found on Earth, earning it a name derived from the Greek word for the sun. Arthur Eddington's famous 1919 eclipse expedition, which measured the deflection of starlight passing near the sun and found it consistent with Einstein's general theory of relativity, is one of the iconic moments in the history of physics. And eclipses continue to provide scientifically valuable opportunities to observe the corona under conditions not otherwise available from Earth, though spacecraft like SOHO and STEREO now provide continuous coronagraph observations from space. The Parker Solar Probe represents the current frontier of direct solar investigation. Launched in August 2018 and designed to make repeated close passes of the sun using a series of Venus gravity assists to gradually lower its perihelion. The spacecraft made history on December 24, 2024, by passing only about 3.8 million miles, roughly 6.1 million kilometers, above the sun's visible surface. At that closest approach, it was moving at about 430,000 miles per hour, faster than any human-made object had ever traveled. It was close enough to sample the near-sun environment directly, where the solar wind is still being accelerated and the corona's magnetic structure is much less processed by distance. At these close distances, the spacecraft has sampled conditions in the corona directly, measuring the solar wind's properties, the local magnetic field, and the dust and energetic particle environment in ways impossible from greater distances. Its observations have already revealed surprising fine-scale structure in the solar wind, including the switchback phenomena, abrupt reversals of the magnetic field embedded in the solar wind, that have challenged existing models and are generating significant theoretical discussion. The Solar Orbiter, a joint European Space Agency and NASA mission launched in February 2020, complements Parker Solar Probe's measurements by providing high-resolution imaging of the solar surface and corona from changing viewing angles. In 2025, after tilting its orbit out of the ecliptic plane, Solar Orbiter returned world-first views of the Sun's polar regions, areas crucial for understanding the solar magnetic field and the solar cycle, but difficult to study from Earth's usual equatorial viewpoint. Together, these two missions are transforming our understanding of the corona, the solar wind, and the connections between surface magnetic activity and the phenomena that pervade the heliosphere. The May 2024 geomagnetic storm was a reminder that space weather is not an abstract hazard. Auroras were seen at unusually low latitudes. Satellite operators had to respond to changes in atmospheric drag as Earth's upper atmosphere expanded under solar heating. Radio communication and navigation systems experienced disturbances. None of this meant civilization was close to collapse, but it showed how connected modern systems are to conditions on the sun. A solar eruption leaves the sun, crosses tens of millions of kilometers, strikes Earth's magnetic environment, changes currents in near-Earth space, and the effects can reach power systems, satellites, aviation, and communication networks. This is the strange modern relationship with the sun. Ancient societies depended on it for agriculture and seasons. Modern civilization still depends on it for climate, food, and water, but also has an additional vulnerability. It has filled near-Earth space with technology. Satellites orbit above the atmosphere. GPS timing underlies banking, navigation, shipping, aviation, agriculture, and telecommunications. Power grids stretch across continents. Space weather is therefore both ancient and modern, the old star interacting with new infrastructure. The challenge is prediction. We can observe active regions. We can estimate when the sun is more likely to produce flares. We can detect a coronal mass ejection after it happens. But predicting the exact timing, direction, magnetic orientation, and Earth impact of a major solar eruption remains difficult. A coronal mass ejection with a magnetic field oriented one way may produce only modest effects. With the opposite orientation, it can couple strongly to Earth's magnetosphere and drive a severe storm. The difference matters enormously, and it often cannot be known with confidence until the eruption is already close to Earth. This is why spacecraft positioned between Earth and the Sun are so valuable. They provide warning, but the warning may be measured in tens of minutes to hours for some key parameters. For power grids, satellites, aviation, and astronauts, even a short warning can matter. The sun's storms are natural events. The scale of their consequences depends on how prepared the civilization beneath them is. Understanding the sun in detail has profound practical importance that extends beyond scientific curiosity into the operations of modern technological civilization. Space weather, the varying conditions in the near-Earth space environment driven by solar activity, represents a genuine operational hazard for a civilization that depends heavily on satellite communications, GPS navigation, high-voltage power grids, and aviation over polar routes. The interconnectedness of modern infrastructure means that a major geomagnetic storm could potentially have cascading effects across multiple systems simultaneously. A sufficiently powerful coronal mass ejection aimed at Earth, comparable to or exceeding the 1859 Carrington event, could induce geomagnetic currents strong enough to damage or destroy large numbers of electrical transformers, components that take months to years to manufacture and are not stockpiled in large quantities anywhere. The economic costs of a major space weather event have been estimated in the hundreds of billions to trillions of dollars in potential damages, making space weather prediction an area of active investment by meteorological agencies, power utilities, satellite operators, and government defense and civil emergency organizations worldwide. Improving space weather prediction requires better understanding of the physical processes responsible for solar flares and coronal mass ejections, particularly the ability to predict not just that active regions on the sun might produce events, but when a specific event will occur, how large it will be, and in what direction it will be aimed. Current prediction capability is limited. We can identify regions of enhanced activity probability days in advance, but specific event timing is generally only predictable minutes to hours ahead, barely enough warning for some types of mitigation. Improved solar observing capabilities, particularly coverage of the sun's far side, which is not observable from Earth and from which a coronal mass ejection could travel to Earth without any warning, would significantly extend useful prediction windows. Radiation exposure is also a concern for human spaceflight beyond Earth's protective magnetic field. Astronauts on the International Space Station, while in low Earth orbit and still largely protected by Earth's magnetosphere, receive significantly higher radiation doses than people on Earth's surface, an exposure that accumulates over long missions and contributes to increased cancer risk. Astronauts traveling to the Moon, or eventually to Mars, would be outside Earth's magnetic protection and directly exposed to the full solar wind and galactic cosmic ray flux, with the additional hazard of solar energetic particle events, short, intense bursts of radiation produced by solar flares and coronal mass ejections that can deliver dangerously high radiation doses in short periods. Planning human exploration beyond Earth orbit requires monitoring and predicting solar activity to enable crews to shelter in more heavily shielded regions of spacecraft during the most hazardous events. The relationship between the sun and life is not just about warmth. Life on Earth is a way of managing solar energy. Plants, algae, and cyanobacteria capture a tiny fraction of incoming sunlight and store it in chemical bonds. Animals eat that stored energy directly or indirectly. Weather redistributes solar heat. Oceans absorb and move it. Ice reflects it. Clouds modulate it. Forests, deserts, plankton blooms, monsoons, winds, and ocean currents are all parts of a planet-sized system responding to the uneven arrival of sunlight. Even the absence of sunlight matters. Day and night created rhythms that biology learned to use. Circadian clocks evolved in response to the rotation of a planet under a star. Seasons shaped migration, reproduction, hibernation, flowering, and human agriculture. The sun does not simply provide energy, it provides timing. It gives Earth cycles, and life has organized itself around those cycles for billions of years. This is why the sun's apparent ordinary repetition is so important. Every sunrise is part of a stable astronomical pattern. The star shines, Earth rotates, Earth orbits, seasons repeat, and biology builds expectations around those repetitions. Life is not only made possible by energy, it is made possible by reliable energy. The sun also shaped the atmosphere indirectly. Oxygenic photosynthesis used sunlight to split water and fix carbon, eventually releasing enough oxygen to transform the planet. The ozone layer formed from that oxygen and then shielded the surface from much of the most damaging ultraviolet radiation. In this way, life used sunlight to build protection from sunlight. The relationship is not simple dependence, but feedback. Star, atmosphere, ocean, rock, and biology influencing one another over geological time. The sun's relationship with life on Earth goes deeper than simply providing light and heat. The sun has been the driver of biological evolution itself in subtle and profound ways. The sun's ultraviolet radiation is the primary energy source driving photochemistry in Earth's atmosphere, including the production and maintenance of the stratospheric ozone layer. The ozone layer absorbs most of the sun's harmful UVB and UVC radiation, protecting surface life from the mutagenic and lethal effects of these short wavelength photons. The evolution of this protective ozone layer was itself partly driven by biological activity. The Great Oxidation Event approximately 2.4 billion years ago, when photosynthetic bacteria produced enough oxygen to transform Earth's atmosphere from reducing to oxidizing, also created the conditions for ozone formation, providing a feedback between biology and the solar atmospheric system that made the ozone layer a biological product as much as a physical one. Photosynthesis, the biological process by which plants, algae, and certain bacteria convert sunlight into chemical energy, releasing oxygen as a byproduct, is the foundational energy source for essentially all life on Earth. The evolutionary innovation of oxygenic photosynthesis, which captures the energy of visible light to split water molecules and reduce carbon dioxide to organic compounds, was one of the most transformative developments in the history of life, transforming the atmosphere, enabling the evolution of complex multicellular organisms that could exploit the energy-rich oxygen atmosphere, and establishing the fundamental link between solar energy and biological productivity that has persisted for over 2 billion years. Solar energy drives the water cycle that distributes fresh water across Earth's surface, evaporating water from the oceans, driving it inland as atmospheric moisture, depositing it as rain and snow, and allowing it to flow back through rivers to the sea, carving landscapes, transporting nutrients, and providing the fresh water that all terrestrial life depends on. Solar energy drives atmospheric circulation, the differential heating of different latitudes, and the resulting temperature gradients that drive winds, ocean currents, and the global circulation patterns that determine climate and weather. Solar energy, accumulated over hundreds of millions of years in organic matter that was compressed and transformed by geological processes, is what we burn as fossil fuels, the accumulated sunlight of ancient ecosystems stored chemically and now being released in geological instants, fundamentally altering the atmospheric composition and heat balance of the planet that depends on the sun for everything. The future sun also gives us a useful way to understand habitability. A habitable planet is not simply a planet at the right distance from its star. It must remain at the right distance, around the right kind of star, with the right atmosphere and geological feedbacks for long enough. The habitable zone moves as a star evolves. For the sun, it has been slowly moving outward because the sun's luminosity has been slowly increasing. Earth has remained habitable not because the sun never changed, but because Earth's atmosphere, oceans, carbon cycle, and geology have helped regulate surface conditions while the sun brightened. That regulation has limits. As solar luminosity continues to rise, chemical weathering will draw down carbon dioxide. Plants will eventually struggle, the biosphere will simplify, oceans will evaporate, and the moist greenhouse threshold will become unavoidable. The end of Earth's habitability is therefore not a sudden red giant catastrophe. It begins much earlier, with the star still looking much like the sun we know, only brighter than Earth's climate system can comfortably tolerate. This gives the Sun's story a strange emotional shape. The same slow stellar evolution that gave Earth enough time for life will eventually end the conditions for that life. The Sun is not hostile in this. It is not benevolent either. It is simply evolving according to stellar physics. Habitability exists in the temporary overlap between a star's life, a planet's orbit, and a planet's ability to regulate itself. And that overlap, for Earth, has been astonishingly long. Oceans persisted. Continents moved. Atmospheres changed. Life altered the chemistry of the planet. The Sun brightened, but not too quickly. For billions of years, the balance held. The Sun will not last forever. In approximately 5 billion years, a timescale so vast that it meaningfully exceeds the total current age of the universe, the hydrogen fuel in the Sun's core will begin to run out. As the core hydrogen becomes depleted, the core will contract and heat, while hydrogen burning will shift to a shell around the core. The extra energy from shell burning will cause the outer layers of the Sun to expand dramatically, and the Sun will begin its transition from main sequence star to red giant. During the red giant phase, the Sun will expand to roughly 100 to 200 times its current diameter, large enough that its surface will approach or possibly reach Earth's current orbital distance. The exact fate of Earth is uncertain and depends on details of the Sun's mass loss rate during the red giant phase. As the Sun loses mass through its greatly enhanced stellar wind, Earth's orbit will expand, potentially keeping ahead of the expanding solar envelope. Most models suggest, however, that Earth will ultimately be engulfed, not violently or dramatically, but gradually, as the expanding solar surface surrounds Earth's orbit and the drag from the low-density outer solar atmosphere causes the planet to slowly spiral inward. Whether the physical rock of Earth survives the engulfment or whether it is disintegrated into the solar envelope depends on details that current models cannot fully resolve. Before the red giant phase begins, however, the habitability of Earth's surface will already have been lost. As the Sun continues its gradual brightening over the next billion years, the additional solar energy received by Earth will push the planet toward a runaway greenhouse state, the same fate that transformed Venus into its current uninhabitable condition. Within roughly 1 billion years from now, Earth's oceans will begin to evaporate, initiating a feedback cycle of increasing water vapor and greenhouse warming that will eventually produce conditions incompatible with any known biology on the surface. 1 billion years is not soon in any human sense. It represents about 70% of the current age of the Earth, or about 6 times the span from the first complex multicellular life to the present. But it is finite. The habitability of Earth, the conditions that allow liquid water and biological activity, are not eternal features of the solar system. They are the product of a particular configuration of the Sun's luminosity, Earth's orbit, and Earth's atmospheric and geological systems. A configuration that has persisted for billions of years, but that will not persist indefinitely as the Sun continues its slow, inevitable brightening. Understanding this eventual fate and understanding the path the Sun will travel through its red giant and subsequent white dwarf phases is not a morbid or defeatist exercise. It is part of the larger project of understanding how stars work, how planetary systems evolve, and what the long arc of cosmic time looks like when traced from the formation of a star through its full life cycle. The Sun is roughly halfway through its main sequence lifetime, about 4.5 billion years burned, about 5 billion remaining. By the standards of human history, it is solidly middle-aged. And middle-aged means, by any measure, a great deal of time remaining. The Sun also gives meaning to the differences between the planets. Mercury is not merely small and airless. It is a world living close to the Sun, where solar radiation is intense, where the solar wind has direct access to a surface without a thick atmosphere, and where the sky is black even at noon because there is no air to scatter the sunlight. Its days are strange, its temperature swings extreme, and its surface records billions of years of exposure to a harsh inner solar system environment. Venus is what happens when sunlight, atmosphere, and greenhouse physics move into a runaway state. It receives more solar energy than Earth, and its thick carbon dioxide atmosphere traps heat with extraordinary efficiency. Its surface is hot enough to melt lead, not because it is the closest planet to the Sun, Mercury is closer, but because its atmosphere transformed incoming sunlight into a planetary-scale thermal trap. Venus is therefore not only a planet. It is a warning about atmospheric feedback. Earth sits in the middle, not perfectly safe, not guaranteed, but balanced for an unusually long time. It receives enough sunlight to keep water liquid, but not so much that oceans immediately boil. It has an atmosphere thick enough to regulate temperature, but not thick enough to become a Venus-like furnace. It has a magnetic field that helps protect the atmosphere from direct erosion by the solar wind, and it has geological cycles that have helped regulate carbon dioxide across deep time. Mars shows another kind of solar relationship. It is farther from the Sun, colder, smaller, and no longer protected by a global magnetic field. The solar wind has interacted with its upper atmosphere for billions of years, contributing to atmospheric loss. Mars may once have had rivers, lakes, and perhaps a thicker atmosphere, but today it is a cold desert under a pale Sunday. The same star shines on all three rocky worlds, but distance, atmosphere, mass, geology, and magnetic protection decide how that sunlight becomes climate. Beyond Mars, the Sun becomes weaker with distance, but it never becomes irrelevant. Jupiter receives far less sunlight than Earth, yet its upper atmosphere, auroras, and moons still exist within the Sun's radiative and magnetic environment. The icy moons of the outer planets are lit by sunlight, so weak that noon there would feel like deep twilight on Earth, yet even that distant light matters for surface chemistry. Comets spend most of their lives frozen in darkness, then approach the Sun and awaken, their ices sublimating into glowing comas and tails shaped by sunlight and solar wind. A solar system is therefore not simply a set of planets around a star. It is a gradient of sunlight, temperature, radiation, and magnetic influence. Each world is partly defined by how much of the Sun it receives, how it responds, and what it can hold on to under that influence. The Sun is also a tool for measuring the universe. Because it is nearby, astronomers can study its spectrum in extraordinary detail. Fraunhofer lines, dark absorption lines in the solar spectrum, revealed the chemical fingerprints of elements in the Sun's atmosphere long before the internal physics of stars was understood. Each line corresponds to atoms or ions absorbing light at specific wavelengths, and together they form a code. Hydrogen, helium, sodium, calcium, iron, magnesium, and many other elements leave their signatures in sunlight. The discovery of helium is one of the most beautiful examples. In 1868, during a solar eclipse, astronomers observed a spectral line in the Sun that did not correspond to any known element on Earth. The element was named helium, after Helios, the Greek sun. It was discovered in the Sun before it was isolated on Earth. In that moment, spectroscopy turned the Sun from a source of light into a chemical object that could be analyzed across space. Spectroscopy also revealed that the Sun is not made primarily of the same material as Earth's surface. Early assumptions placed too much weight on familiar rock-forming elements because those were familiar from terrestrial chemistry. Modern astrophysics showed that the Sun is overwhelmingly hydrogen and helium, with heavier elements making up only a small fraction of its mass. Those heavy elements are still crucial. They affect opacity, energy transport, planet formation, and the chemical inheritance of the solar system. but they are trace ingredients in a star built mostly from the two simplest elements in the universe. This is part of a larger pattern. The sun teaches humility. The matter most familiar on Earth, rock, metal, water, air, organic chemistry, is not the dominant matter in the cosmos. The universe is mostly hydrogen and helium, and the sun is a local example of that cosmic abundance. Earth is chemically rich because earlier stars enriched the gas from which the sun formed. The sun carries that history in its composition. The sun's rotation is another reminder that it is not a solid body. Earth rotates once as a unit, more or less. Mountains, oceans, and atmosphere move relative to each other, but the solid planet has a coherent rotation. The sun is plasma. Its equator rotates faster than its poles. Different depths rotate differently. The convection zone and radiative zone do not share the same pattern. This differential rotation is not a minor detail. It is essential to the dynamo that builds the magnetic cycle. A solid star would have a simpler magnetic field. A plasma star with differential rotation twists, stretches, and amplifies magnetic fields continuously. The result is an object whose surface changes in ways that record deeper motion. Sunspots drift in latitude over the cycle, producing the famous butterfly diagram when their positions are plotted over time. Early in a cycle, sunspots appear at higher latitudes. As the cycle progresses, they appear closer to the equator. This pattern is one of the observational signatures of the solar dynamo unfolding beneath the visible surface. The butterfly diagram is beautiful because it turns disorder into pattern. Individual sunspots are irregular. Active regions appear, split, grow, decay, and rotate out of view. But across years, their collective behavior reveals the cycle. The sun is not random. It is turbulent with memory. Solar prominences show another side of that magnetic control. These immense arcs and curtains of plasma, suspended above the surface by magnetic fields, can extend tens or hundreds of thousands of kilometers into the corona. They are cooler and denser than the surrounding coronal gas, which makes them visible in certain wavelengths as dark filaments against the solar disk or bright structures at the limb. A prominence is matter held in the star's atmosphere by magnetic architecture. When that architecture becomes unstable, the prominence can erupt, sometimes becoming part of a coronal mass ejection. Seen in ultraviolet and hydrogen alpha light, the sun is no longer a smooth disk. It becomes a landscape of loops, filaments, bright active regions, dark coronal holes, spicules, waves, eruptions, and flows. The familiar yellow-white photosphere is only one face of the star. At different wavelengths, different layers and processes appear. X-rays show the hot corona. Ultraviolet shows the transition region and chromosphere. Radio waves reveal energetic particles and magnetic processes. Neutrinos come from the core. No single image of the sun is the sun. Each wavelength is a different way of listening. Neutrinos are especially important because they escape from the core almost immediately. Photons take a long, random path through the solar interior, but neutrinos barely interact with matter at all. Once produced in fusion reactions, they fly outward through the sun almost as if the entire star were transparent. They reach Earth about 8 minutes later, carrying direct information from the nuclear furnace at the center. This makes solar neutrinos extraordinary messengers. Every second, tens of billions of them pass through each square centimeter of Earth's surface, and almost all pass through the entire planet without touching anything. Detecting them requires enormous underground detectors, shielded from cosmic rays and designed to catch the rare interaction when a neutrino finally does collide with matter. The fact that we can detect any of them at all is a triumph of experimental physics. The solar neutrino problem, which lasted for decades, was one of the most productive mismatches in modern science. Detectors saw fewer electron neutrinos than expected. Either the sun was not working as models predicted, or neutrinos were doing something unexpected. Helioseismology supported the solar models. The eventual solution, neutrino oscillation, the transformation of one neutrino flavor into another during flight, showed that neutrinos have mass and that particle physics needed revision. A problem that began with the sun became a discovery about the fundamental particles of the universe. This is another reason the sun matters beyond solar physics. It is close enough to serve as a laboratory for nuclear reactions, plasma physics, relativity, particle physics, magnetism, and climate. The nearest star is not a single subject. It is a meeting point for many branches of science. The sun's light also carries information about motion. When material on the sun moves toward or away from us, its spectral lines shift slightly through the Doppler effect. By measuring these shifts, astronomers can map flows on the surface and in the atmosphere. They can see plasma rising and sinking in granules, material moving along magnetic loops, waves passing across the surface, and rotation carrying one limb toward us while the other moves away. The sun is not static even in still images. Its spectrum shows motion everywhere. The same principle used to measure solar motion is used across astronomy. Doppler shifts reveal exoplanets tugging their stars, galaxies receding as space expands, gas orbiting black holes, and stars moving around the Milky Way. Again, the sun is the nearby classroom in which techniques used across the universe can be tested and refined. The sun is also responsible for shadows, and shadows are part of how life understands the world. A shadow is simple on the ground, but physically it is evidence of geometry. Light traveling in straight lines from an extended star, blocked by an object, projected onto another surface. The changing length of shadows across a day gave ancient people a way to measure time. The shifting height of the sun across seasons gave them a way to measure the year. Sundials, calendars, solstices, equinoxes, agricultural timing, navigation, architecture, and ritual landscapes all grew from the predictable geometry of Earth under sunlight. This cultural history is not separate from the physics. It is the human response to a star's regularity. The sun made time visible before clocks existed. It drew moving lines across stone, sand, walls, and fields. It turned astronomy into survival knowledge long before astronomy became a mathematical science. Even now, with atomic clocks and satellites, the underlying rhythms remain solar. Civil time is adjusted to Earth's rotation. Seasons remain orbital. Agriculture still depends on light, temperature, and rainfall. Human bodies still respond to the daily cycle of brightness and darkness. Technology changes the tools, but the basic structure remains: a rotating planet under a steady star. There is also danger in too much sunlight. The same ultraviolet radiation that drives atmospheric chemistry can damage DNA. The same visible and infrared energy that warms Earth can, under the wrong atmospheric conditions, push a planet toward dangerous heating. The same solar particles that create auroras can damage electronics and tissue. Life on Earth exists not simply because the sun shines, but because Earth filters, moderates, and distributes that energy. The atmosphere scatters blue light, absorbs dangerous ultraviolet, traps some infrared, circulates heat, and creates weather. The magnetic field deflects much of the solar wind. Oceans store and move heat. Clouds reflect sunlight and trap warmth. Ice reflects strongly, creating feedbacks. Vegetation changes surface reflectivity and water cycling. A habitable planet is not a passive recipient of sunlight. It is an active regulator of stellar energy. That regulation is fragile on some scales and robust on others. Earth has survived asteroid impacts, ice ages, volcanic episodes, atmospheric transformations, and changes in solar brightness. But it has done so through feedback systems with limits. Push those systems too far, and a planet can shift into a different state. Venus and Mars are reminders that sunlight alone does not guarantee habitability. The planet must be able to handle the star. The Sun's future white dwarf phase is also part of the story. After the red giant phase, after the outer layers are shed into space, the Sun's core will remain as a white dwarf, a dense, Earth-sized remnant composed mostly of carbon and oxygen, no longer powered by fusion, gradually cooling over immense timescales. The outer layers lost by the dying Sun will form a planetary nebula, not because it has anything to do with planets, but because early telescopes saw such objects as round, planet-like disks. For a time, that nebula will glow as ultraviolet radiation from the hot, exposed core ionizes the surrounding gas. Then the gas will disperse into interstellar space, carrying material processed by the Sun back into the galaxy. The white dwarf will remain, cooling slowly, fading from white to yellow to red to black over timescales longer than the current age of the universe. In that distant future, the solar system will no longer be the system we know. The inner planets may be gone or transformed. The outer planets will orbit a much dimmer remnant. The habitable warmth of the main sequence Sun will be over. But the matter of the Sun will not vanish. Some will remain locked in the white dwarf. Some will drift into space, part of the galaxy's long recycling of material. The Sun was born from enriched interstellar gas, and it will return enriched gas to interstellar space. It is not only a giver to Earth. It is part of the Milky Way's chemical circulation. This completes the larger pattern. Stars form from gas. They shine. They build elements. They shape planets. They create environments where life may arise. They evolve. They die. They return material. Later stars and planets inherit what earlier stars made. The Sun is our star, but it is also one chapter in that galactic process. There is a final layer to the Sun's importance. It connects the smallest physics we know to the largest structures we live inside. At the smallest level, the Sun depends on quantum mechanics. Protons in the core repel one another electrically. Classically, many of them should not have enough energy to overcome that repulsion and fuse. But quantum tunneling allows a tiny fraction of them to pass through the barrier. That tiny probability, multiplied by the immense number of protons in the core, becomes the steady fusion power of the Sun. A quantum effect, repeated on stellar scale, lights a planet. At the level of atoms, the Sun is a spectroscopic object. Its light carries absorption lines that reveal composition, temperature, pressure, motion, and magnetic fields. The splitting of spectral lines in magnetic fields, known as the Zeeman effect, lets solar physicists measure magnetic structures on the surface. The broadening of lines reveals thermal and turbulent motion. The shifting of lines reveals rotation and flows. The Sun's spectrum is not just color. It is an encoded physical report. At the level of plasma, the Sun is a moving, conducting fluid shaped by magnetic fields. It is not solid, not liquid, not gas in the ordinary sense, but ionized matter where electrons and ions move freely, interact with fields, and create collective behavior. Plasma is the most common state of ordinary matter in the visible universe, and the Sun is the nearest plasma laboratory. Studying it helps explain not only stars, but also nebulae, accretion disks, jets, the solar wind, planetary magnetospheres, and the intergalactic medium. At the planetary level, the Sun is climate, chemistry, and time. It powers evaporation, atmospheric circulation, ocean currents, photosynthesis, and the seasonal rhythms around which life has organized itself. It provides the energy gradient that makes Earth's surface active. Without sunlight, Earth would not be a blue planet with moving air, liquid water, forests, storms, and metabolism. It would be a frozen body radiating its internal heat slowly into darkness. At the solar system level, the sun is gravity and structure. It determines the orbits of the planets and the broad architecture of stable zones, resonances, asteroid belts, comet reservoirs, and planetary migration histories. The early sun, surrounded by a disk of gas and dust, was the center around which worlds assembled. The present sun is the central mass around which those worlds continue to move. At the galactic level, the sun is one star among hundreds of billions, born from interstellar material enriched by older stars. It carries the chemical history of the Milky Way in its composition. Its planets formed from the same disk, inheriting that chemical mixture. Earth is therefore not simply a product of the sun, but a product of the sun's place in a galaxy that had already lived long enough to make heavy elements. And at the human level, the sun is the object that made observation possible. Daylight allowed landscapes to be seen. Shadows taught geometry. Seasons taught prediction. Eclipses taught celestial mechanics. Spectra taught chemistry. Sunspots taught that the heavens were not perfect and unchanging. Solar neutrinos taught that particles could change identity. The sun has been a teacher at every scale. This is why the sun can carry an entire episode by itself. It is not only a star. It is an intersection between quantum physics and weather, between plasma and biology, between ancient calendars and spacecraft, between the beginning of the solar system and the future loss of Earth's habitability. The more carefully it is studied, the less it resembles a simple bright disk. There are also limits to what the sun can tell us. It is one star with one mass, one age, one chemical composition, one planetary system, and one particular magnetic history. To understand stars in general, astronomers compare it with many others: red dwarfs, orange dwarfs, hotter F-type stars, massive blue stars, giants, white dwarfs, young T-Tauri stars, old metal-poor stars, flare stars, binary systems, and stars with planets very different from our own. The sun is the nearest example, not the complete sample. But precisely because it is close, it anchors those comparisons. If stellar models cannot reproduce the sun, they cannot be trusted for distant stars. If solar abundances are revised, models of stellar structure and galactic chemical evolution must adjust. If helioseismology reveals discrepancies in the interior, opacity calculations and composition estimates must be re-examined. The sun is ordinary, but it is also the standard against which ordinary stellar physics must be tested. This creates a beautiful tension. The sun is not special in the galaxy, but it is special to knowledge. It is not rare, but it is irreplaceable. It is one star among countless stars, yet it is the only star close enough for us to study as a place rather than a point. Seen from another star system, the sun would be faint. From a few dozen light years away, it would be one modest point among many, perhaps interesting only because of the small rocky planet in its habitable zone with unusual atmospheric chemistry. From Earth, it is overwhelming. Perspective changes everything. Science tries to hold both perspectives at once. The sun is our star, but not the center of the universe. It is ordinary, but not simple. It is stable, but not static. It is life-giving, but not safe. It is familiar, but not fully understood. That combination is what makes it worth studying slowly. One of the most useful things the sun teaches is that stability is an active condition. From a human distance, stability can look like nothing happening. The sun rises, sets, rises again. Its brightness seems constant. The seasons return. The system feels fixed. But inside the sun, stability is maintained by motion, pressure, reaction, transport, and correction. Fusion is continually responding to pressure and temperature. Convection is continually moving energy outward. Magnetic fields are continually being stretched and rearranged. The corona is continually losing energy and being reheated. The solar wind is continually escaping. The whole system persists because processes are running, not because processes have stopped. Earth's dependence on the sun works the same way. A stable climate is not a motionless climate. It is moving air, moving water, moving carbon, moving heat, clouds forming and dissipating, ice growing and melting, organisms taking in energy and releasing it, rocks weathering, oceans absorbing, and the atmosphere circulating. The sun powers many of these motions, and life exists inside the pattern they create. This is why the idea of the sun as a calm object is incomplete. The sun is calm only in the average sense. Its total output is steady compared with many other stars. Its main sequence evolution is slow. Its position at the center of the solar system is gravitationally stable. But on its surface and in its atmosphere, there is no calm at all. Plasma rises and falls. Magnetic loops twist. Flares erupt. Particles accelerate. Waves propagate. The corona streams outward. The calm we experience on Earth is mediated calm. It is filtered by 93 million miles of distance, by the inverse square spreading of radiation, by Earth's atmosphere, by the magnetosphere, by oceans, by clouds, by the carbon cycle, and by the fact that human lifetimes are short compared with stellar evolution. We do not live next to the sun as it truly is. We live at the one distance, around the one kind of planet, where its violence has been softened into daylight. That softening is the story of habitability. A star does not need to be gentle to support life. It needs to be steady enough, at the right distance, with the right planetary protections, for energy to become usable instead of destructive. The sun is not gentle. It is enormous, hot, magnetically active, and slowly evolving. But Earth receives it through layers of moderation. The atmosphere filters. The oceans buffer. The magnetic field shields. The biosphere adapts. The result is a planet where stellar energy can become forests, storms, rivers, food, oxygen, and thought. There is something powerful in that. The same nuclear furnace that would destroy anything brought too close becomes, at the right distance, the source of almost everything alive. The sun also reminds us that the solar system is not isolated from the galaxy. The heliosphere moves through the local interstellar medium as the sun orbits the Milky Way. The solar wind pushes outward. The interstellar medium pushes back. The shape of the heliosphere is influenced by the sun's motion through galactic gas and magnetic fields. Cosmic rays from outside the solar system enter the heliosphere and are partly modulated by the solar cycle, meaning that solar activity helps regulate the high-energy particle environment reaching Earth. So the sun is both local and galactic. It dominates the solar system, but it travels through the Milky Way. It shields us from some galactic cosmic rays, but it was itself born from galactic material. It creates a bubble around its planets, but that bubble moves through a larger interstellar environment. Home is nested, Earth inside the magnetosphere, magnetosphere inside the solar wind inside the heliosphere, heliosphere inside the galaxy. The sun is the center of our immediate world, but not the edge of the story. There is one last practical truth about the sun. We are still learning how to live with it. For most of history, human exposure to the sun was immediate and local. Too much heat could dry crops. Too little light could shorten growing seasons. Storms and seasons shaped food supply, and eclipses interrupted expectation. Modern civilization has added a new layer. We now place machines in orbit, send spacecraft beyond Earth's magnetic protection, depend on radio signals moving through the ionosphere, and run electrical systems long enough to respond to currents induced by geomagnetic storms. We have extended our infrastructure into the sun's environment. That means solar knowledge is no longer only astronomy. It is risk management. It is engineering. It is planning for satellites, astronauts, airlines, power grids, communication systems, navigation, and the increasingly crowded region of near-Earth space. A better forecast of solar activity can protect hardware. A better understanding of radiation can protect crews. A better model of the solar wind can protect missions traveling to the Moon, Mars, and beyond. But even this practical concern leads back to wonder. The star that ancient people tracked with stones and shadows is the same star now monitored by spacecraft, coronagraphs, magnetometers, neutrino detectors, radio arrays, and helioseismic instruments. The tools changed. The dependence did not. We are still, in the deepest sense, a planet under a star. There is also a human reason the sun is difficult to understand clearly. It is too present. Objects that are rare often receive attention. Eclipses, comets, supernovae, and auroras feel special because they interrupt expectation. The sun does the opposite. It returns every morning. It is so reliable that it disappears into the category of background. We notice weather more than sunlight, clouds more than the star behind them, sunset colors more than the nuclear engine producing the light. Science reverses that habit. It takes the ordinary and makes it physical again. The sunrise becomes planetary rotation. Warmth becomes photon absorption. Daylight becomes radiation from a photosphere. A sunspot becomes a magnetic flux tube suppressing convection. An aurora becomes charged particles guided into the upper atmosphere by magnetic fields. A solar cycle becomes the visible trace of a dynamo operating inside a rotating plasma sphere. The sun is therefore a lesson in scale, but also in attention. The most important object in the sky is not always the one that feels most mysterious. Sometimes the deepest object is the one so constant that we stop asking what it is. One more way to understand the sun is to see it as a clock running at several speeds at once. At the surface, granules appear and disappear in minutes. A flare may release its energy in seconds. A coronal mass ejection can cross the distance to Earth in a day or two. Sunspots grow and decay over days or weeks. The solar rotation carries active regions across the face of the sun in about a month. The sunspot cycle rises and falls over 11 years, while the full magnetic polarity cycle takes about 22. Deeper inside, the timescales become longer. Energy wanders outward from the core over thousands of years. Helium accumulates over billions. The core slowly changes composition. The luminosity gradually rises. The sun's main sequence lifetime stretches across 10 billion years, and its red giant future lies billions of years ahead. All of these clocks are the same star. The sun is fast in its atmosphere, slow in its evolution, steady in its energy output, restless in its magnetism, immediate in its daylight, and ancient in the processes that produce that daylight. It is the nearest example of a class of objects that build galaxies, regulate planetary climates, and create the chemical conditions from which planets and life can emerge. This is why the sun can never be only a familiar disk in the sky. It is a star close enough to feel, close enough to endanger technology, close enough to study in detail, and close enough that every living system on Earth is already part of its story. The sun also gives us a way to understand how knowledge itself changes. For most of human history, the sun was known by experience: warmth, light, season, shadow, drought, harvest, sunrise, sunset. Then it became an astronomical object, measured in angular size and apparent motion. Then it became a physical body, with composition revealed by spectroscopy. Then it became a nuclear furnace, explained by fusion. Then it became a plasma system, structured by magnetism. Then it became a source of particles, fields, waves, and space weather. Then, through neutrinos and helioseismology, it became an object whose hidden interior could be tested. Each stage did not erase the previous one. The sun is still warmth and light. It is still sunrise and season. But it is also nuclear physics, plasma physics, magnetohydrodynamics, particle physics, planetary climate, and stellar evolution. Science does not make the sun less familiar. It makes the familiar deeper. This is the best reason to return to the sun as a subject. Not because it is exotic, but because it is so close that we assume we understand it before we do. The nearest star still contains unsolved problems. The ordinary morning sky still opens into the physics of the core, the corona, the heliosphere, the Earth's climate, and the far future of the solar system. The sun is not a mystery because it is hidden. It is a mystery because it is visible every day and still not exhausted by visibility. And still, after all the measurements, the sun remains partly unresolved. The corona is still not fully explained. The solar wind is still not perfectly understood at its source. The exact details of the dynamo that sets the strength of future solar cycles remain difficult to predict. The connection between small magnetic events and large eruptions is still being refined. The sun is close enough to study continuously, yet complex enough to resist complete prediction. That is not a failure of science. It is the nature of a real star. A real star is not a diagram. It is an immense, turbulent, magnetic, nuclear, radiating object with processes interacting across scales from particles to planetary distances. The fact that it is familiar does not make it finished. The sun gives us daylight. It also gives us a frontier. That frontier is unusually intimate. Most astronomical frontiers are distant. Black holes, exoplanets, galaxies, the early universe. The sun is different. It is a frontier that touches the face, warms the ground, powers the wind, and appears every morning through ordinary windows. It is at once cosmic and domestic, distant enough to be safe only because of space and atmosphere, close enough that every change in its activity belongs to the environment of Earth. To study the sun is therefore to study the nearest piece of the universe that is bigger than our world. And that is enough. The nearest star does not need to be exotic to be profound. It only needs to be understood clearly as matter, energy, gravity, magnetism, time, climate, danger, protection, origin, and future, all shining from the same familiar place in the sky. For now, the sun remains what it has been for all of human history. The star at the center, the source of daylight, the engine of weather, the power behind photosynthesis, the maker of seasons, the driver of space weather, and the future red giant already hidden inside the calm disk we see each morning. It is ordinary by the standards of the galaxy. It is everything by the standards of Earth. And we leave it there, bright, violent, stable, changing, indifferent, and absolutely necessary. Good night.